Go.
Okay, so I'm going to show you how you put the leads on a patient. So you want to have your patient in lateral cumbency. You also want to have the legs not bent or not too stretched out, but kind of in a straight perpendicular to the body. And so we're going to first place the first lead, which is white, on the right front here on the skin. And you just kind of take it and you just clip it on. And then you place the other lead. So the way to remember it is snow over grass and smoke over fire. And so from white to the black lead, that represents lead 1. From white to the red lead, that represents lead 2. And then from black to red, that represents lead 3. And it basically helps you measure and determine the mean electrical access in your electrical current of your heart. And there are other things that you can figure out with the leads is like the AVR, the AVL, and the AVF. But if you want more information, there is a great diagram in Duke's that will explain that all to you. Thanks.
So today I'm going to tell you about the mean electrical axis. And what this is, it's a vectorial representation of ventricular depolarization. So it's a sum of all of the waves of depolarization that are occurring simultaneously. So in veterinary medicine, we typically use a hexaxial lead system, which is comprised of 6 leads. The standard multi-lead system includes leads 1, 2, and 3, which are 1, 2, and 3. And these are all bipolar leads, which means they have a positive and negative pole. And then you have the augmented voltage leads, and those are AVR, AVL, and AVF. So AVR, AVF, and AVL. And those are unipolar and only have one positive pole. So what this picture is representing is it looking at the heart straight on. So this is at the center of the heart, and this is the atria and the ventricle. And so since your depolarization is generated in your atria and is going away from your atria to your ventricle, all of your vectors here will be negative, and since they're going away from this area, and they'll be positive down here because they're going toward the ventricle.
Okay, go.
Okay, so now we're going to determine our mean electrical axis. But the first thing we need to do in order to do that is to determine what our coordinates would be. And this is generally how we will end up doing it. So in real life, you'll have a nice printed out ECG graph on grid paper showing you the different leads on the patient that you just took the ECG from. And for now, we've just created leads 1 and 2. And so basically, as you can see here, we have lead 1 and lead 2. Lead 2 probably looks more familiar. We have a P, Q, R, S, and T wave, our typical ECG complex there. So in order to get our coordinates, what we basically have to do is take the positive waves of the QRS complex and subtract them from the negative waves for both leads 1 and 2. So for lead 1, our R wave, the height of our R wave is, we're saying roughly 3 millimeters. When this is printed out on grid paper, it'll be more exact and easier to determine. All I have to do is count the different squares that are printed on the paper. And for our S wave, which would be our negative wave, in this case we have 0 millimeters. So we take the difference and we get 3 millimeters. That's going to be our first coordinate for our mean electrical axis. For lead 2, we're going to do the same thing, but we have to take into account the Q wave as well, because that's going to be a negative wave. So in this case, our R wave is about 10 millimeters, our Q wave is about 0, and our S wave is actually more substantial than the lead 1 was, and it's about 3 millimeters. So we take the difference of that, 10 minus 0 minus 3, we get 7 millimeters, and that's our second coordinate for our mean electrical axis.
Okay, so now we're going to take our measurements from our lead 1 and lead 2 that we just calculated, which is the 3 and 7 millimeters, and we're going to graph them. The benefit of graphing it is that we can determine where all of the depolarizations are occurring in the heart that's most likely, and it's typically going to be in your left ventricle, and I can show you how we've graphed it. So we take the lead 1 for 3 millimeters, so this is the direction of lead 1, so we go over 3 millimeters, and we put a dot there. And then our lead 2 was 7 millimeters, and lead 2 is at a diagonal. Ideally, you would measure this out completely with a ruler. We didn't have one, so we estimated, and so lead 2 was here. So what you do is you draw a line straight down from the 3 millimeters, and you draw a line down to your dot for lead 2, and then you do a perpendicular. And as soon where these two intersect, that is the direction of your arrow. And so anywhere between 0 and 160 is normal in a dog, and anywhere between 40 and 100 is normal in a cat. So as you can see, this arrow is pointing between 60 degrees, which is lead 2, and 90 degrees, so that would be normal. So if this arrow was pointing in any other direction, it could lead us to an area of the heart that is having abnormal pathology going on.